Section: Introduction. In this section, we will discuss our exploration of reducing the number of layers needed for each token by exiting early during inference. Unlike methods like quantization or sparsity, reducing the number of layers does not require specialized hardware or software kernels. We also combine early exiting with speculative decoding to propose a self-speculative decoding approach that does not need an additional model or auxiliary layers. Our contribution is an end-to-end solution that involves a training recipe combining layer dropout and early exit loss. This results in more robust inference, allowing for exiting at earlier layers and creating different-sized submodels within the same model. Our self-speculative decoding solution decodes with earlier layers and verifies and corrects with later layers, achieving speedups between 1.341 to 2 depending on the task. To motivate our approach, we investigate what happens in each layer of a large language model, LLM, using an example prompt. By analyzing token predictions across layers, we observe that earlier layers often provide irrelevant predictions, while later layers lead to the final prediction. We find that most of the time, the final token prediction occurs fewer layers before the end, indicating the potential for early exiting to save computation. Our goal is to make LLM models require fewer layers to predict each token and reduce unnecessary computation. We propose layer dropout during training, with higher dropout rates for later layers and lower rates for earlier layers to make the model less reliant on later layers. Additionally, we introduce a loss function during training to improve the understanding of embeddings from earlier layers by the LM heads. Unlike previous approaches, we use a shared LM head for all transformer layers, making training faster, more memory efficient, and simplifying deployment and maintenance. This allows us to train a model equivalent to an ensemble of models of various depths, capable of skipping from different transformer layers to the LM head. Section Summary. In this section, we investigate the challenges of deploying large language models, LLMs, to different devices due to high computational costs. We propose a novel approach that combines layer dropout during training with early exiting during inference to reduce the number of layers needed to predict each token, resulting in faster and more efficient inference. By strategically skipping layers and training a shared LM head for all transformer layers, our solution achieves significant speedups of up to 2 times depending on the task, without requiring specialized hardware or software kernels. Section: Correcting if we exit too early. In this section, we explore the concept of correcting early exits in deep learning models. Whether we use heuristics, predictors, or modify the training process to enable models to predict early, exiting early during inference may reduce accuracy. It would be beneficial to verify the accuracy of an early prediction and correct it by processing the remaining layers. Some methods have proposed using a confidence heuristic to determine if the remaining layers are necessary after an early exit. Here, we utilize speculative decoding techniques to validate and rectify early exit predictions. Speculative decoding is a technique that speeds up the generation of tokens by verifying groups of tokens simultaneously, rather than generating each token one by one. We introduce a self-speculative decoding approach where we use early exit to generate tokens sequentially and then verify groups of tokens in parallel using the remaining layers. Dropout, a technique that randomly sets a portion of output elements to 0 during training, was initially introduced to prevent overfitting. In the context of convolutional neural networks, CNNs, dropout was commonly used before batch normalization became popular. However, with the rise of transformer models, dropout made a comeback with a dropout rate of 0.1. The regularization effect of dropout stems from enabling training across multiple models and introducing noise to node activations, making the model more robust to data distribution shifts. Layer dropout, also known as stochastic depth, involves skipping layers during training. This technique has been explored in various models, including ResNets and language models, to improve robustness and speed up training. Early exit strategies have been investigated in different model architectures, such as encoder-only, encoder-decoder, and decoder-only models, to improve efficiency during both training and inference stages. Speculative decoding is a popular method for accelerating language models by verifying groups of tokens in parallel. Our proposed self-speculative decoding approach leverages a draft model to generate tokens and a main model to verify and correct them, allowing for faster inference without sacrificing accuracy. Compared to existing methods, our approach enables efficient reuse of intermediate layers, leading to improved performance in early exit scenarios. Section Summary. In this section, we explore the concept of correcting early exits during inference to maintain accuracy in deep learning models. We introduce a self-speculative decoding approach that leverages speculative decoding techniques to verify and correct early exit predictions by executing remaining layers in parallel. Our method differs from previous approaches by using a shared exit for all layers, allowing for efficient reuse of activation and KV cache during the verification and correction stages. Section: Proposed Solution. In this section, we present our approach, which consists of three main stages: training using layer dropout and early exit loss, inference using early exit, and correction using speculative decoding. We will explain each stage in detail in the following subsections. In the first stage, training using layer dropout and early exit loss, we start by representing the input tokens as 5 number 5 and the output as 6 number 6 in a transformer model. This model includes an embedding layer that converts token indices to token embeddings, denoted as 7 number 7, and consists of 8 number 8 transformer layers. Each transformer layer 9 number 9 evolves the embeddings from the previous layer, 10 number 10, and a final LM head maps the outputs of the last layer, 11 number 11, to logits, 12 number 12. We use a binary cross-entropy loss function, denoted as 13 number 13, for training language models. One modification we introduce is layer dropout, where we apply dropout to the transformer layer at each iteration. The dropout rate, denoted as 16 number 16, determines the probability of dropping samples within a batch. By applying this dropout operation, we aim to enhance training speed. Additionally, we incorporate early exit loss at each layer during training to improve prediction accuracy of lower layers. This involves supervising the model to connect early exit layers to the LM head directly. To manage the early exit loss effectively, we introduce a normalized per layer loss scale, 33 number 33, and a binary curriculum function, 35 number 35, to determine when to enable early exit at each layer. We experiment with different curricula, such as rotational and gradual early exit curricula, to optimize training efficiency and accuracy. Moving on to the second stage, inference using early exit, during autoregressive decoding, we run the initial 47 number 47 transformer layers in the model and then proceed directly to the LM head for generating each token. We vary the number of transformer layers considered during decoding and present the corresponding accuracies in the results section. Section Summary. In this section, we introduce our approach consisting of three stages. Training involves layer dropout and early exit loss, inference utilizes early exit verification, and correction employs speculative decoding. During training, we implement layer dropout to enhance model performance by dropping samples within a batch and applying transformer operations accordingly. Additionally, we incorporate early exit loss at each layer to supervise the model and improve prediction accuracy, using a curriculum to control the scale of early exit loss across layers. Section: Inference using self-speculative decoding. In this section, we explore how we can enhance autoregressive generation by incorporating self-speculative decoding. By utilizing layer dropout and early exit loss during training, we discovered that we can accelerate the generation process by exiting early. However, this speedup comes at the expense of accuracy compared to using the full model. Speculative decoding offers a solution to this dilemma by leveraging a faster but less accurate model to expedite generation without sacrificing accuracy. Nonetheless, this approach necessitates maintaining and training two separate models, leading to increased memory and training demands. To address these challenges, we introduce a new self-speculative decoding algorithm that combines early exit with a novel approach to reduce memory usage by utilizing a single model. This algorithm also minimizes latency by reusing hidden states in both drafting and verification stages. Our self-speculation algorithm comprises two main steps: self-drafting and self-verification. In the self-drafting step, we use early exit to generate a set of draft tokens, while in the self-verification step, we employ the full model to validate these draft tokens and predict the next token in a single pass. To facilitate reuse of information between these steps, we introduce a cache reuse technique that merges the KV cache with storing the exit query. This integration allows us to streamline the process and optimize memory usage. In the self-drafting phase, we generate an initial set of draft tokens using early exit, referred to as speculations. By training the model once, we obtain a range of candidate draft models at different layer depths, enabling us to evaluate the trade-off between latency and accuracy. Moving on to the self-verification stage, we leverage the full model to verify the draft tokens and identify any discrepancies. By only computing the remaining layers not utilized in the drafting phase, we streamline the verification process and ensure efficient utilization of resources. Furthermore, we optimize computation efficiency by reusing the KV cache between the draft and verification stages. By sharing the first layers of the model in both steps, we reduce memory overhead and latency. Additionally, we introduce an exit query cache to further minimize computation by storing the query vector of the exit layer for seamless continuation from the draft to the final layer. In our experiments, we evaluate the effectiveness of our training approach across various scenarios, including continual pre-training, pre-training from scratch, fine-tuning on code data, and task-specific dataset fine-tuning. We explore different training setups and report our findings to validate the efficacy of our self-speculative decoding algorithm. Section Summary. In this section, we introduce a novel self-speculative decoding algorithm that combines early exit and speculative decoding to speed up autoregressive generation without sacrificing accuracy. By leveraging a single model and reusing hidden states, our algorithm reduces memory usage and latency compared to traditional speculative decoding methods that require storing and training two models. Through self-drafting and self-verification steps, we demonstrate how our approach optimizes the process by efficiently reusing the KV cache and exit query cache, resulting in improved efficiency and performance in autoregressive transformers. Section: Early Exit Inference Results. In this section, we assess the outcomes of our early exit inference experiments. After training each model setup, we check the accuracy of exiting early at different layers. We first focus on continual pre-training. We display our findings for Llama 2 7B and 13B across various evaluation tasks and compare them with the baseline model. Zooming in on specific accuracy values for the last and middle layers of each model, we observe that LayerSkip performs better than the baseline for earlier layers. For the last layer accuracy, LayerSkip shows only a slight decrease compared to the baseline. Notably, certain classification tasks maintain decent accuracy on earlier layers in the baseline model, while open-ended generation tasks drop significantly. Surprisingly, the performance drop from the last to the middle layer is minimal for challenging tasks like classification. This could be due to the nature of these tasks, where errors in generating one token can impact the accuracy of subsequent tokens. LayerSkip proves to be crucial for generation tasks, significantly improving accuracy. Moving on to pre-training from scratch, we present results for Llama 2 1.5B and 7B pre-trained from scratch on a diverse set of evaluation tasks. Introducing our layer dropout configuration and early exit loss leads to higher accuracy on earlier layers compared to the baseline. While there is a slight drop in accuracy on the last layer for some tasks, in others, our configuration results in higher accuracy. For fine-tuning on code data, we compare the accuracy of LayerSkip with a baseline model on two coding tasks. LayerSkip performs better for earlier layers, showing a significant improvement on one task when combined with layer dropout and early exit loss. The last layer accuracy with LayerSkip remains similar to the baseline. In the case of fine-tuning on task-specific dataset, we evaluate the performance of our Llama 1.5b model on a specific training set with and without LayerSkip. We find that with LayerSkip, early exit inference improves significantly, although there is a slight decrease in accuracy on the final layer. We then delve into our self-speculative decoding results, evaluating the algorithm on different trained models. Quality metrics such as exact match, M, and Rouge 2 are reported, along with token acceptance rate and throughput. Speedup compared to autoregressive decoding is also calculated. Continuing with continual pre-training, we evaluate Llama 2.7b and 13b with and without LayerSkip on various tasks. Speedups are observed, with higher speedups for the smaller Llama 2.7b model. In pre-training from scratch, we find that the bigger model achieves a higher speedup compared to the smaller model, surpassing traditional speculative decoding. For fine-tuning on code data, we evaluate our code fine-tuned Llama 1.7b model and observe a speedup with no accuracy drop. Lastly, in fine-tuning on task-specific dataset, we present results for Llama 1.5b fine-tuned on a training dataset and evaluated on a test set, showcasing the M on the full test set and latency experiments. Section Summary. In this section, we assess the impact of early exit inference on various model configurations by evaluating accuracy at different layers after training. We compare the performance of models with and without LayerSkip on diverse evaluation tasks, noting that LayerSkip shows significant improvement on generation tasks while maintaining minimal accuracy drop on classification tasks. Additionally, we explore the benefits of layer dropout and early exit loss in enhancing accuracy on earlier layers, with some tasks showing improved performance compared to the baseline model. Section: Ablation Studies. In this section, we conducted ablation studies to investigate how the accuracy of the last and middle layers changes over time when pre-training from scratch. We performed 3 training experiments on Llama 1.5b with varying numbers of tokens and displayed the results in a figure. Each experiment ran for 50,000 steps, with a batch size of 4 per device, a context window of 4096, and different numbers of GPUs, 32, 64, 128. We examined the perplexity of a held-out split of the stack on the last layer, layer 24, and the middle layer, layer 12. As expected, the perplexity on the last layer decreased as we trained on more tokens. Surprisingly, we observed a significant increase in perplexity on the last layer during training, which could be mitigated by applying early exit loss or layer dropout. This finding suggests the need for further research on transformer dynamics and the evolution of embeddings across layers during training. Our training approach aims to maintain high accuracy in earlier layers while minimizing the drop in the last layer's accuracy. Additionally, we introduced the use of KV cache for self-speculative decoding to enhance model generation speed. Our experiments showed that employing KV cache consistently saved 9 to 20 milliseconds per token, depending on the task. However, our self-speculative decoding solution has some limitations. It requires fine-tuning a model or pre-training it using our recipe, unlike the approach proposed by others that does not involve changing a model's weights. Tuning hyperparameters such as layer dropout, early exit thresholds, and learning rates is crucial to prevent a decrease in last layer accuracy when pre-training from scratch. Finding the optimal learning rate for maintaining accuracy can be challenging and time-consuming.